Okay, thank you very much for the invitation. And now what happens? There we go. Okay, this is the plan of the talk. So the first part will be about the paper I wrote with postdoc at the University of Washington, Chi-Hung Wu. And the second part will be about another paper I wrote with a graduate student, Xiaoyi Shi, like here somewhere. And then I will conclude with some future directions. So I will skip most of the introduction other than just mentioning what the Hartle-Hawking Wavefunction is. So we want to compute the initial conditions for the universe, and Hartle-Hawking instructed us to do a path integral over all geometries that in the future connect to the end of inflation and the reheating surface. For simplicity, in what I'm about to describe, I will consider a universe that is just pure de Sitter without the inflaton. And in the simplest realization, we consider a universe with an S3 spatial topology. And in that case, the geometry that dominates the Hartle-Hawking path integral is the global DS4, where in the future we have an expanding three-sphere. And to make the geometry smooth, in the past we go along the real-time axis, and then we turn to the imaginary axis and cap it off in the south pole of the Euclidean half-sphere. Just a comment that will be relevant later. This is usually this counter is chosen so that the metric is real in both Lorentzian and Euclidean segments, but for example, when one adds the inflaton, there is no way to make the solution real everywhere. So then it makes sense to just think of more generally as a geometry that goes from the south pole in some complex contour that is continuously connected to this one. And trying to make it real is a kind of a red herring from pure de Sitter. Okay, so the probability of creating this universe is the exponential of the on-shell action, which is 3 pi over g Newton lambda. And at the classical level, this is also the, since the real part of the action comes from the Euclidean evolution, this is also the exponential of the action on the Euclidean de Sitter that is S4. In inflation, one has to be a little bit more careful, and that was done in the past. And the upshot is that the cosmological constant is replaced by the potential at the beginning of inflation. This has some phenomenological issues pointed out, I think, first by Vilenkin and then nicely reformulated by Maldacena, which I'm not going to address in this talk, but I just wanted to mention it. Okay, so instead what I will discuss is what is the probability of inflation, maybe sort of related to the previous talk, of creating a universe with a non-trivial spatial topology. Since S4 is the maximal volume geometry, we might expect that S3 will be the most likely, but we will see that it's not that straightforward. The simplest case one can study was considered by Laflamme a long time ago, which is the probability of creating a universe with a topology S1 cross S2. After Laflamme, this was studied in several papers that here I mentioned some of them. So what I'm about to describe is based on a paper written with Maldacena and Yang in 2019, and well, I will describe the recent developments from earlier this year. So in this case, from simplicity, we want to compute the Hartle-Hawking wavefunction of a universe that in the future consists of an round S1 cross S2 that is exponential with a size that is exponentially increasing. But now, other than this overall size, we have two parameters. One is L, is the size of the S1 parameterized by this coordinate X. And another relevant parameter is, well, alpha, which essentially tells you that as you go around the circle, the sphere goes to itself up to a rotation. And these are, of course, there are deformations, but these are the ones that become the most subtle when computing the wavefunction. But for simplicity in the talk, I will just set alpha to 0 and just look at S1 cross S2. Okay, in this case, the geometry that contributes to this boundary condition in the future is this geometry. Is essentially the Schwarzschild-de Sitter geometry, where the radial direction is interpreted as time. Okay, so this is what it is. So you saw it in, well, the charged version in Douglas talk. And if this time becomes very large, then this sphere and the circle grow at the same rate. Here, the t square is the dominant one. And this t hat is related to the exponential of the FRW time. As you go into the past, you need, according to Hartle-Hawking, to smoothly cap it off somewhere. And this happens at the location where this f is 0, where the temporal circle contracts. Not the temporal, sorry, the spatial X circle contracts. And for that contraction to happen smoothly, this t hat initial has to be somewhere in the complex plane given by this formula. And this parameter mu that in the Schwarzschild-de Sitter interpretation would be the mass also has some complex value. There are other solutions, and there is some subtlety about other solutions, but just for simplicity, since I only have 35 minutes or so, I will ignore that. So I will just take the one that we feel is we believe is the physical one. Okay. So the problem with this wave function is at the classical level, if we compute the on-shell action, well, it has this behavior. So when the size of this one is small, this goes to 0, which is fine. But then as we increase the size of this one circle, it saturates at some value that is the exponential of 2/3 of the de Sitter entropy, or 2 pi over g Newton lambda. This happens to be the action of gravity on S2 cross S2, which that will be important later. But the important thing here is that it's independent of L. The L dependency is subleading at large L. Yeah. This leads to a problem, because when we compare the probability of creating this universe to the probability of creating an S3 universe, in S3 we get the exponential of 3 pi over g Newton lambda. But for this universe, we get something that seems to make sense, but we also need to integrate over L, because all the lengths of the circles are equally likely. In this limit, we get a divergence. So naively, it seems like the probability of creating this universe is infinitely more likely than the S3, which certainly sounds a little weird. And here is a 1 over L related to a question in Douglas' talk about 1 over beta. There is a similar reason why there is a 1 over L, but it's not enough to, from the measure, sorry, but it's not enough to fix the problem. So in this paper, based on models of de Sitter JT gravity, we proposed a resolution of this problem. There are large quantum corrections that introduce new L dependence in this prefactor. This is related to Misha's talk in the context of near-extremal black holes. And in this paper, we tried to prove it directly in Einstein gravity. That's what I'm about to describe. Okay. So to analyze quantum gravity corrections, we will start with a one-loop calculation of the wave function of the universe. So this is the path integral. G is this metric, this complex metric that I just wrote down, and H is the quantum fluctuation. So to read in order, we get the classical answer with some one-loop determinant. Here, the geometry is complex. The eigenvalues of this operator delta L, which is like the propagator of the graviton, including gauge fixing terms and everything, it's complex because the background metric is complex. So it's not even about positive or negative, you just get complex numbers. So when you choose the counter, you'll get the absolute value dominated by the absolute value of the spectrum of this propagator. And then the phase will be much more complicated than in the other talk, but it's kind of irrelevant because I'm computing the wave function. So it can be complex, there is no problem with that. The classical prediction is accurate only if the spectrum of this operator is gapped. But we will see that in this S1 cross S2 geometry, when the size of this one becomes very large, there are modes where the eigenvalues of the propagator become arbitrarily small and proportional to 1 over L. And that's where the new L dependence appears. And again, this is the same, it's a different scenario, but it's the same principle that the one controlling the large quantum corrections of the near extremal charge black holes in Misha's talks. In that case, the role of L is played by beta. And the quantum corrections also become large at low temperatures because you have modes that are arbitrarily light which are related to the length of the throat in the extremal limit. Okay, so to do it in Einstein gravity, we will analyze the spectrum of this propagator. That's a complicated problem, but one can argue that the lowest lying modes are in the S-wave sector, so we will take these ansatz, where we have some momentum in the S1 circle that I call Kn, parameterized by some integer n. And then we have 4 functions, F1, F2, F3, and F4, that are functions of time only. So we will analyze the eigenvalue equation of the propagator with these ansatz. And when you gauge fix using the transverse traceless condition, these 4 functions are reduced to 1, and the problem is reduced to an ODE. And then it's much simpler than the higher dimensional. And one can do this this is in the S-wave sector where the dominant contribution is, but one can do it for any spherical harmonics. Actually, I might not mention it later, but there is also similar light modes in the L equals 1 sector. But because of time, I will skip that. Okay, so then what we did was to extend the numerical analysis in this paper that did exactly this for the near extremal black hole, using this collocation method. to this setup and evaluate the leading quantum corrections. And the main technical complication of this case with respect to the Risen-Nordstrom black hole is the fact that the geometry is complex. Makes it more interesting. The first manifestation of this problem is that I told you that the geometry is a contour that goes from initial t hat to infinity, but which contour should you take? For concreteness, we took this one. So we write t hat in terms of a real parameter c. When c is -1, you're at, sorry, this should be t hat I at the initial t hat. And when this c goes to +1, this blows up and you go to +infinity. So the -1 to 1 real interval is mapped to a contour that goes from t hat initial to infinity. So then we have a complex metric, but now in real coordinates, and you can formulate the problem better. And you might ask, okay, what's special about this particular contour? Well, we can show analytically and verify numerically that the spectrum of the propagator is independent of the contour as long as the contours are related by continuous deformations. If they are not related by continuous deformation, the spectrum doesn't have to be the same. And this is interesting because it means that all these geometries should be identified in the gravitational path integral, and it would be wrong to treat them as different geometries, although they are not technically connected by a diffeo, unless maybe one complexifies what one means by diffeomorphism. Okay, so for each n bigger than 2, we got this result. So we get a lot of modes that are order 1 in the Sitter radius units. But then there is a special mode for each n that vanishes as 1 over L. So this is the interesting one. I'm just showing one plot, but we can do it for different n's and different partial waves. So the upshot is that there are eigenvalues that for large L take approximately this form. And I didn't want to use this perspective in this talk, but if you are familiar with JT gravity, this is precisely the action of the Schwarzschild modes in JT gravity with imaginary coupling, which we argue in the paper with Madsen and Yang is the correct description of this limit. Yeah, and the quantization of these light modes affect the classical approximation of the wave function. I'm not going to go over the derivation, but there is essentially a power of L for each of these modes, just like in the Schwarzschild. And then there's an overall power of L from zeta function regularization on this sum over these modes. And yeah, there was a paper doing something similar, but that was doing something only in the near horizon by Blacker, Castro, Sibesman, Toldo from earlier this year. I think what they're doing is different, but I wasn't able to pinpoint exactly what the difference is. But well, this is definitely related. Okay, so after these quantum corrections are included, the wave function takes this form. So this is the classical answer I wrote before. This L to the 6, well, yeah, you can believe me, it comes from zeta function regularization of these modes. If you're familiar with JT gravity, you shouldn't find this surprising. Maybe the 6 is partly because of these spin 1 modes that I didn't discuss. There is some power of G Newton lambda with some C1 and C2 that I didn't compute. But since here we're computing the absolute value square, these are automatically positive. Now, the nice thing about this expression is that this probability distribution has a peak at the square root of the Sitter entropy. And now the integral over L is finite. And again, it's of the order of the exponent of the on-shell action on S2 cross S2, which is what we expected. In inflation, this calculation was done by Busso and Hawking, and they get essentially the same. You get this answer, but with lambda replaced by the potential at the beginning of inflation. Yeah, so this is interesting. Even though the probability distribution ends up being the exponential of the classical action on S2 cross S2, if you want to obtain that from the wave function, you need to include quantum corrections. So it's an interesting feature. Okay, so that's the first part. The second part is, well, like I say, it's about this paper with Shoichi, and also there was a related paper by Ivo, Maldacen, and Sun doing, well, the same calculation I'm about to describe, but with a very different motivation, I believe. So, okay, we showed, well, the first part is well known, the norm of creating an SD-1 universe. Now I will generalize to any dimension because it's easy. The norm of the Hartle-Hawking wave function is given by the path integral on the Euclidean de Sitter, which is the sphere. For an S1 cross SD minus 2 universe, the norm is the path integral on S2 cross SD minus 2. So it would be interesting to extend this connection to the quantum level. But before doing this, motivated by this paper by Juan from last year, we decided to look at the phase of the path integral first, since if the norm is related to the path integral on these spaces, we expect it to be real and positive. Well, this is from a bit of repeat what Douglas said. So it's well known that from a long time that if you do the Euclidean path integral, there is a negative mode that causes a phase due to contour rotations that you need to make the integral convergent. First calculation was done, careful calculation was done by Polchinski and got this I to the d plus 2. So we want to do it for other geometries such as Nariai, or to see if the norm of the wave function is still compatible with this calculation on these closed Euclidean spaces. Okay. So I will sketch a little bit the derivation of the phase. So it ends up being that we can compute the phase for any solution of Einstein's equation. So I will sketch roughly how calculation goes. The first comment I want to make is that you can take the fluctuations in the metric and expand it in this way. The first term, phi mu nu, is the transverse and traceless component. The second term is a pure diffeo, these two terms. This pure diffeo can be decomposed in a Hodge decomposition with a divergence-free vector and a pure gradient. And finally, H is the total trace of the metric fluctuation. So we want to do the integral over H mu nu by decomposing into an integral over phi mu nu, this eta mu, chi, and H. But obviously, not all these modes on the right-hand side contribute. The original path integral is over H. So if we have a mode on the right-hand side that doesn't produce a fluctuation in the metric, then that's not even a zero mode. It's just a mode that doesn't contribute, doesn't participate in the path integral. To see that, it's useful to rewrite the fluctuation in this way. So we have the TT component. This part doesn't change. It's just proportional to H mu nu. We have the pure vector diffeo. This one contributes to the metric fluctuation unless this eta happens to be a Killing vector. Then this right-hand side is zero, and it's just a mode that doesn't exist in the gravitational path integral. For this scalar diffeo, we can combine it with the trace to write it this way. And components of chi contribute unless this operator, it's in the kernel of this operator. This happens when this chi is just a constant. In that case, the gradient is just zero. Or when it's not a constant, but this non-trivially vanishes, in which case it's a non-isometric conformal Killing vector. So it's a conformal Killing vector that is not itself a Killing vector, because all the Killing vectors are automatically divergence-free. So we will do a path integral over these modes and try to look at where the negativities are. Then we need to add the gauge fixing. So this is the gauge fixing term that will impose our transverse gauge. The tensor mode and the vector modes are decoupled from each other, but we have two scalar modes, H and chi, so they can couple to each other. But one can see that if this coefficient of the gauge fixing term is tuned to this beta that appeared in the gauge fixing condition, then the coupling between H and chi can be removed, and then the two scalar fields are decoupled from each other. This is not intended to be obvious, it's just something that comes from the calculation. So for simplicity, we will take this relation between gamma and beta, and our gauge fixing condition will be parameterized by just one coefficient gamma. Okay, so this is the Einstein action with the gauge fixing term. This is the TT component. Delta 2 is the Lichner-Horowitz operator. It's a generalization of the Laplacian acting on transverse traceless tensors. Delta 1 is a similar one acting on vectors, and delta 0 is just minus the Laplacian. And then in the scalar components, there are two operators that are useful to define, this delta tilde 0 and delta tilde gamma. This one is independent of the gauge fixing, and this one depends on the parameter gamma. And all these operators that appear here are positive at short distances, other than these minus lambda terms. So there's only a finite number of terms, finite number of modes of these operators that are negative. So that's useful, that will be useful in a minute. Another useful fact that one can show is that the product of delta 0 and delta tilde 0 is non-negative, And when it's 0, it's either because the mode is a constant or because it's a conformal Killing vector. So that's why this delta tilde is special. So again, the goal, just like in Douglas' talk, is to identify the negative modes and rotate the contour. So I will go over the different sectors. The first is the TT mode. So this one there is nothing universal I can say about it, other than we have to rotate the contour for each negative mode of delta 2. Okay, so an example is in the context of black hole, where the negative mode of the TT, negative mode in the TT sector of, for example, a small black hole is related to the fact that this black hole is physically unstable, thermodynamically unstable, which is found by Grossberg and Jaffe, and Douglas also reviewed in his talk. There are bounds one can derive for this delta 2, but they're not useful enough to claim that it's either always positive or negative. Okay, and doing the contour rotation for the negative modes gives a factor of I to the number of negative modes of delta 2. The vector modes are trivial. They have this form in the action, in the Einstein action, so you see it's an operator square, so it's not negative. The 0 modes are also trivial because one can show that a 0 mode of delta 1 is a Killing vector, so you don't have to, it doesn't even appear in the path integral. And there is a good reason why this action is manifestly positive, which is that the only contribution to the action for the vector modes come from diffeomorphisms. They come from the gauge fixing term. So if I pick my gauge fixing action to be positive, then there's not going to be any negative mode in this sector. Now, the most problematic sector is the scalar one. So we have the scalar diffeos and the trace of the metric. Yes. So the idea, as I said, all these operators that I defined are positive and short distances. So this chi action doesn't seem to have any problem at short distances, but the action for H becomes negative at short distances because of this minus sign. So what one can do is first rotate the contour for H to minus I H prime. So this fixes the UV behavior. And then H prime and chi have a positive spectrum up to a finite number of modes. And then we can look at this action with the plus sign here, which I copy here again. So in this case, like I said before, there is a useful fact that one can show. I can say how to prove it, but it's not super important. One can show that this combination of differential operators is always positive, and when it's 0, it's because the mode didn't participate in the path integral. So the only problem is to find the negative modes of this delta tilde gamma. Okay, which if you remember, should have copied it here, but when you replace here delta tilde, there is this minus lambda term, which can, so delta 0 is positive, and this minus lambda term can make the some modes of delta tilde gamma be negative. Okay. Okay. Now the contour for chi, if we have a negative mode of delta tilde gamma, has to be rotated with a minus I, just like we did for all the other components of the metric. But if we have a negative mode of H prime, we need to rotate it backwards with a plus I, because it's a mode that we shouldn't have rotated to begin with. And in our paper, we only consider this possibility. I think in Madacena and Ivo and Sun paper, they consider other possibilities too. But I don't know, we didn't. So in this case, since this delta tilde gamma appears in both chi and H, if chi has a negative mode, H also has a negative mode, and then the phase will cancel. Now, the only case where the phase doesn't cancel is when we have a negative mode in H prime because of delta tilde gamma, which would be a negative mode of chi, except for the fact that it's a mode that doesn't participate in the path integral. So if you have a mode of chi that is a negative mode, but it's also a 0 mode of delta delta tilde, then that mode was not included in the path integral to begin with, and then it doesn't contribute to any factor of I. So then the powers of I just come from the number of modes that are negative modes of delta tilde gamma that happens to be in the kernel of this delta delta tilde. So so that the phase comes from H prime, but the chi mode partner doesn't play any role. Now, as I said, there is this theorem that not the theorem, sorry, the 0 modes of these operators are either constant or conformal Killing vectors. And one can plug this into the definition of delta tilde gamma and check that whenever there is a non-isometric conformal Killing vector, well, the constant mode, they always have a negative eigenvalue of delta tilde gamma. It's always minus something positive times lambda. So the power of I appearing from the scalar modes, it's always 1 plus the number of non-isometric conformal Killing vectors. So this is a generalization of what Douglas described for any geometry, any solution of Einstein's equation. Okay. For the sphere, this reproduces the result of Polchinski. So the number of conformal Killing vectors is d plus 1. So the number of scalar negative modes is 1 plus d plus 1, which is d plus 2. And in the sphere, you can check that delta 2, the spectrum in the TT sector doesn't have any negative mode. But, well, like I said, more generally, one can claim that the phase on any solution other than the sphere to the vacuum Einstein's equation with positive curvature, it's always minus I to the n2 minus 1 minus the number of non-isometric conformal Killing vectors. Just to mention it, in the case of, let's say, black holes in ADS, like the small black hole in ADS, all the scalar modes, so because of, sorry, I will go back a little bit. Because this minus lambda becomes positive, there are no modes that are negative after doing the contour rotation of H. So then these two terms disappear, and the total phase is I to the N2. And then that makes sense, because whenever there is a physical instability in the black hole, it will come with a factor of I. But when we're working with positive curvature, then we get these extra contributions. Okay, so my goal was to apply this to the norm of the S1 cross SD minus 2 wave function. In that case, there are no non-isometric conformal Killing vectors, so N0 is just 1. There's only one factor of I from the scalar sector. But the delta 2, the propagator acting on the TT component, has one negative mode. And this was found a long time ago by Ginsberg and Perry. The negative mode is essentially a mode where the radius of the where the radius of S2 and SD minus 2 vary independently. So then, because N2 is equal to 1, and there are no conformal Killing vectors, the phase becomes trivial, and the argument of the partition function on S2 cross SD minus 2 becomes just real and positive. Let me mention there was a paper by Volkov and Biff a long time ago, which tried to do this and incorrectly concluded that it was imaginary. So their paper was very useful, but we believe that this is the correct answer. And from the point of view of the path integral on this geometry is computing the norm of the Hartle-Hawking wave function, this is a very reasonable result. Let me mention, just to mention it, this also holds for a metric called the Page metric, which is a rotating analog of the Nariai solution. For some reason, some people decided to study the spectrum of delta 2 numerically last year, so then it was easy to just look at it, and they found one negative TT mode, so their partition function is also real and positive. Okay, so in the last few minutes, I will discuss some future directions with Qihong Wu and Xiaoyi Shi, which concerns a different interpretation of the Nariai geometry as nucleating black holes. This was actually the original interpretation of Ginsberg and Perry, and it was also extended by in several papers of Wolfensohn and Hawking from the late 90s. And there was also a nice paper by Susskind a few years ago about the role that the Nariai black hole can play in the Sitter. And according to these works, the rate of black hole pair production would be the ratio of the action on the Nariai geometry and the Sitter, which is exponentially suppressed. And the expectation would be that after the nucleation, the Nariai black hole quantum fluctuations will send it a little bit away from the Nariai limit, and then the instability of Nariai will start an evaporation that will eventually remove the black hole, and you'll go back to empty the Sitter. To make an analogy, this is somehow like the Hawking-Moss instanton. So in this case, you have a potential with two minima, and you start in a vacuum where this is 4 minutes. Okay, that's good. You start in a false vacuum here, where the scalar field has this value FB everywhere in the sitter. And the Hawking-Moss is supposed to describe the decay in this vacuum to this vacuum. And the instanton consists on a solution where you have, again, the sitter, but where the scalar field jumps to the top everywhere. Classically, if the scalar field jumps here, it will stay there forever, but quantum fluctuations will move it a little bit, and then there will be a classical rolling down towards the true vacuum. For this interpretation to make sense, following the usual Coleman and Callan theory of vacuum decay, the ratio of the partition function with the scalar field on the top and on the false vacuum should be imaginary. And this is indeed true in this case, because there is a L0 fluctuation of the scalar that has a negative mode, because, well, this is an unstable maximum. So this phase is compatible with this interpretation. So the analogy with Nariai is that, well, the sitter is roughly here. Then the Nariai black hole is a geometry that is different from the sitter everywhere and nucleates this pair of black holes. So it's like the Nariai black hole is like being at the top of the potential, and then you move a little bit, and then you go back to evaporation and back to the sitter. So the only difference with this picture is that the true vacuum is the same as the place where you started. So in the end, it ends up being a very unlikely fluctuation of the sitter. Unlikely because it's exponentially suppressed. One more comment I wanted to make just for fun about this analogy is that if the curvature of this potential becomes very large, then there are more than one negative mode. There are d+1, because the L=1 harmonic can become negative as well. So this might make you, actually the phase would be I to the d+2, just like the sphere one. So that might make you worry that the interpretation as vacuum decay, now I'm back in the Hawking-Moss context, that might make you worry that the vacuum decay interpretation doesn't work. But when B double prime increases beyond a certain bound, then the Coleman-de-Lucia bubble solution appears. So it starts as a very thick bubble, which as you increase B double prime becomes thinner and thinner, and eventually it eventually becomes the thin wall approximation of Coleman and DeLucia. This transition where the Coleman-de-Lucia starts existing was found by Jensen and Steinhardt, and the value of this transition is exactly the same as the value where these extra d+1 negative modes appear. So presumably the phase is always I for all potentials, and there was a nice paper by Victor Ivo analyzing the opposite limit to this, which is when V double prime is very large, and you look at the negative modes of the Coleman-de-Lucia geometry. Okay, this was side remark. So the interpretation of S2 cross SD-2 as a nucleation rate makes sense if this ratio is imaginary, but that's not what we find. We find that this ratio, let's imagine that we fix the partition function of the sphere to be real and positive, like Maldacena described. This ratio would just be real. So then it's not clear if this is the right interpretation of this geometry. One can add an observer to make this ratio imaginary, but then it seems like the rules it's not clear what are the rules. It looks like you can do whatever you want depending on what answer you want to get. So I just wanted to mention it as an interesting question. Something else we're studying is what happens after the Nariai black hole is nucleated. So there is some exotic behavior found by Bose and Hawking. For example, there is an initial anti-evaporation regime that seems to be very unphysical. So we were revisiting that. We were also looking at whether there are large quantum corrections at the initial moment, similar to the near extremal black hole ones. But the picture we seem to find is that there is no anti-evaporation and no large quantum correction. Instead, this picture of the near Nariai black hole just evaporating and disappearing seems to be the right answer. Okay, so the conclusions. First, we analyzed large quantum gravity corrections that affect this S1 cross S2 component of the Hartle-Hawking wave function of the universe. Then motivated by computing the norm of this wave function, we looked at the phase of the gravity path integral. We were able to compute it for any Einstein manifold, for any solution of pure gravity with a positive cosmological constant. I'm almost done. So an interesting question is whether one can find a non-perturbative prescription to define the integration contour of the path integral, motivated by looking at these negative modes. Finally, I just wanted to mention two ADS-CFT scenarios where the phase is important. Well, one I already mentioned, so I won't repeat it. Another scenario where it's important that I think it's interesting, which is when we compute supersymmetric indices using the gravity path integral, and we can compare with the supersymmetric index in the CFT, in the dual CFT, the geometries that compute the index are complex. They're completely complex in general. Sometimes they happen to be real, but that's very special. I mean, even in Euclidean signature. So we really have complex geometry. So then the one loop determinants will a priori be complex, but on the dual side, we know that these indices would be real and could be positive or negative depending on if most of the states are fermionic or bosonic. But there is a sign that one can compare to the CFT. Anyways, I thought this might be an interesting case study to understand the calculations of the phase a little better, where one can compare to a dual CFT calculation. That's it. Thank you for your attention.
Your first calculation, when you were calculating the determinant that contributed to the wave function, you calculated the contribution to psi, and then you took the square. Would there be a way to do the calculation where you consider first psi bar, and you have some modes that are continuous through the two sides, right? Sort of with in boundary conditions, but you're still fixing L, just one quantity. That would give you directly the things that would be real.
That geometry would probably be singular at the location where you fix the L, right? Because you are fixing some component of the metric there. So it would be like yes. Yeah, I think that's right, but we didn't do that. So it would be like some complex S2 that goes to the future, you fix the length, and then you go back to the past. Yeah, that would be interesting, but we didn't do it. Yeah.
In Douglas's calculation, instead of computing the partition function, as far as I understand, he computed the density of states for an inverse Laplace transform and got something real. Since you have a more general formula for, the power of I in the phase, can you argue that whenever you do an inverse Laplace transform to get an analogous density of states, you get something real? Or do you kind of find examples where you don't get something real?
Let me see.
Can you find examples with different numbers of conformal killing vectors that end up giving you something that's not real after an inverse?
Yes. So yeah, I think an example of that is in the Nariai geometry. Well, first of all, just to emphasize, like you said in Douglas, it was about the states of the sitter, density of states of the sitter. In our cases, we just came to here by thinking about the norm of the wave function. But indeed, I think like I mentioned in the context of Nariai, when you look at S2 cross SD minus 2, the number of negative modes of the particle moving on that geometry depends on the trajectory of the particle. And there you can get, that's why I said, depending how you do the calculation, you can get an I if you want, or you cannot get an I. So I think that case is interesting because it's not clear what the rules are of adding an observer. In the interpretation as computing vacuum, not vacuum, but per production, I think you want to get with the observer, you want to get an imaginary answer. Because you can think that you have an observer in the sitter, and then all of a sudden some black hole was created and then evaporated and disappeared. So yeah, in general, the possibilities there are more possibilities, and it's not clear what the rules are.
I have a question about the production. Yeah. If I have a big inflationary universe, can you think of it can you glue this black hole to an inflationary universe? Like, can you think of it as locally producing this black hole or not?
Yeah, I think. Well, you should ask Raphael. I think that's what they studied in the papers in the 90s with Hawking. What happens when the black holes are created in inflation and how they. Yeah.
Something related to that is if I can think of it in that way, why do I need this factor of I? Why can't I think of it as just the overlap of the Hartle-Hawking wave function with the particle configuration that contains the black hole? Well, the factor of I normally in the usual Coleman story comes from the fact that you are computing some energy and there is an asymptotic time. And then when energy with respect to that time is becoming imaginary, you interpret it as a decay rate. But now when we are talking about the closed universe, why should this factor of I be important?
So in the first part of the talk, when I'm talking about the wave function of the S1 cross S2 universe as a subleading contribution to the Hartle-Hawking wave function, there I wouldn't expect it to be imaginary. I think there it makes more sense to be real. It's just a subleading contribution to the Hartle-Hawking wave function. But in the second case, where you think of it as you have your vacuum and then you have some pair production of black holes, I think that the second calculation, it makes more sense to be imaginary. So then I was using this example because depending on what interpretation you want to give, in one, the real answer is more natural, and in the other one, the imaginary answer is more natural. But I feel, well, we can talk later, but I feel like what you're saying is more similar to the first interpretation where you expect it to be real and positive.
You had this paper, you and Frederick had this paper about these hashtag manifolds in the 4D case. Is this stuff, do you agree with the cases that they had in this paper?
Sorry, what?
Like Leo, Frederick, and I think some students, they had the paper in 4D and they consider these hashtag manifolds and they had a bunch of faces. They had like two faces in general. I don't know the paper, then it doesn't help.
Yeah, I think it's difficult because in general, the manifolds don't have conformal Killing vectors, but the negative modes of this TT, the Laplacian in the TT sector are, you have to do the calculation. Sometimes you can find some bounds, but in general you have to do the calculation. So I don't know if they did that. I think they. Probably does. I mean, if not, okay, I can check.
Okay.